So the next short unit that we're going to go over is the application of a derivative called related rates. And you can see the objectives here. Please copy these down in your 2-column notes. You're going to need to go over several of these examples, but I think you're going to find them to be kind of interesting problems. Here we go. Related rates problems use geometric formulas because you're trying to find the volume, surface area, area. So some of these you'll remember, some of these you won't. There are some in this video, but we'll go over all of them in class. On the next couple of screens, there'll be some classic problems using related rates. So for instance, inflating a spherical object. You can see somebody blowing up a balloon or a ball. And also this motion of a ladder against a wall, right? You could say that the ladder was moving this way, and then this is moving this way as well. So moving down the wall, moving away from the wall, towards the wall, you know, of course there's going to be a limit as to how far you can do that. Reducing an object in size, a spherical object, for instance a jawbreaker or a lollipop of some kind. Creating a cone-shaped pile of gravel, right, that's going to be creating that shape at a particular rate. The height of the cone is going to be changing, the radius of the cone is going to be changing, and also this length here, the slant height of a cone is going to be changing. So here is a method that I came across that has worked really well setting up problems of related rates. And that is really your first challenge, is to determine what information you've been given, and then determine what you need to find, and then find the answer. So basically that's what this is. So the first one is you're going to draw a picture and label everything. If it's a ladder problem or a spherical cone problem or sphere problem or a cone problem or whatever it is, you're going to label all the variables and the constant values. You're going to identify the given rate of change, right? The pile is being created at a particular speed, okay? The rate is found and then how to find it. Then you're going to choose an equation that relates the variables in the problem. Is it a change in volume? Is it a change in area? And so you're going to do that. Eliminate all the variables that have no matching rate. And then the third thing we're going to do is just differentiate both sides of the equation with respect to time. And so once again, these are story problems, so there are going to be rates, so we are going to have to put the units at the end. All right, so let's start our first one. Okay, so the first one, situation 1, is that air is being pumped into a spherical balloon at the rate of 8 centimeters cubed per second. We want to find the rate of change of the radius of the balloon when the radius is 10 centimeters. All right, so we have these 4 parts here. We have given information, what we need to find, when, which is also given information, and then set up our equation. So these are the 4 things that we need to set up, okay? And probably, what I'm sitting here thinking is this probably should have been higher because I'm going to run out of room, but that's all right. So here we go. It says first thing I needed to do was draw a picture. So I'm going to draw a picture of a sphere, which is just a circle that's basically 3-dimensional, okay? I know that it has a radius of 10 centimeters, and then air is being pumped into this at a rate of 8 centimeters cubed per second. All right, so the given is that the air is coming into the sphere at 8 centimeters per second, right? So this is going to be the rate, the volume, right? The volume is changing, the volume is increasing. And so dV dt, the rate at which the volume is changing, is 8 centimeters cubed per second. And it says, find the rate of change of the radius of the balloon, right? So the rate of change of the radius with respect to time when the radius is 10 centimeters. Okay? And then we are changing the volume of a sphere, so we need the volume of a sphere. V equals 4/3 pi r cubed. All right, so these are the 4 things. First thing is given, the volume is changing because air is being pumped into spherical balloon, right? It's getting bigger. It's changing 8 centimeters cubed per second. We want to find the rate of change of the radius when r is 10. And then we also want to use the equation, all right? So the third step then is to find the derivative. So the derivative of the volume is 4 pi r squared dr dt. So I should have probably written it dv dt, right? dv dt, because we know what that is. So dv dt is 8. That was in the given. Equals 4 pi. Pi is not a variable, so I just write pi. R squared, and this is what I'm looking for, is dr dt. So what is the radius? Well, the radius is 10. So that's 100. So this is 400 pi dr dt equals 8. And so I have 8 over 400 pi is dr dt. So that's the rate at which the radius is moving. That would be 2 over 100 pi. And it's moving at a rate of centimeters per second because it's a two-dimensional. So it's centimeters per second. So this is my dr dt. A lot to take in. Let's try another one. So this situation is a ladder 26 feet long leaning against a vertical wall. All right, so I have a vertical wall. Here's the floor. And I have a ladder that's 26 feet. The foot of the ladder is being drawn away from the wall at a rate of 4 feet per second. How fast is the top of the ladder sliding down the wall at the instant when the foot of the ladder is 10 feet from the wall? All right, so that's what we have going on here. We have 26 feet is the hypotenuse of that right triangle. We want to find, I think what I'll do is I'll call this x and this y, and then the hypotenuse I'll just call h, right? So down here, this part given is that h is 26 feet. That's given. And then the dx dt, right, this x value is 4 feet per second. And I want to know how fast y is changing, dy dt, when the ladder is 10 feet from the wall. And I think they mean along the bottom, so when x is 10 feet. All right, so this is a right triangle. So x squared plus y squared is equal to h squared. And so what do we know? Well, we do know that h is going to be 26, right? So we know that that's 26. So we have x squared plus y squared equals 26 squared, right? We take the derivative, 2x, and we're taking it with respect to t. So dx dt plus 2y dy dt equals 0, right? 26 squared equals 0. Okay, so what do we know? Well, we know dx dt is 4. We know x is 10, so let's put in what we know. X is 10, dx dt is 4. We know 2. Do we know y? We may have to think a minute on that. And we want to find dy dt equals 0. Okay, so if we know that x is 10, let me draw my triangle a little better here. We know this is 26. We know x is 10. Can we find this? This is y. Well, 26 squared minus 10 squared is going to be what? Does anybody know? It should be 24. So this will be 24. Right? Pythagorean theorem. 26 squared equals 10 squared, and then you can find y. All right, so when we put all that in there, that's 80 plus 48 dy dt equals 0. Move the 80 over. 48 dy dt is 80 negative, right? So dy dt is going down, right? It's moving downwards. That kind of makes sense that it is negative. So I have negative 80 over 48, which reduces to negative 5/3, and it is feet per second. And there we go. All right, here's our next example. Situation 3, salt is falling in a conical pile at a rate of 100 cubic centimeters per minute. Find the rate of change in the height of the pile when the height is 10 centimeters. The coarseness of the salt is such that the radius is equal to the height. All right, so first thing we do is we think about what is a cone. We know what a cone looks like. Looks like this, right? Cone is three-dimensional. It has a radius. It has a height. It also has a slant height. That makes a right triangle. We may need that sometime. We know that the salt is falling into a conical pile, so the pile is growing. The pile is three-dimensional, so it has volume. So dV dt is going to equal 100 cubic centimeters per minute volume, okay? We're going to find the rate of change in the height. So dH dt when the height is 10 centimeters. And also a given is that the radius is equal to the height. So the volume of a cone is 1/3 pi r squared h, but we've not been given r. There is no r, so we need to substitute for the r. We just want it to be in terms of h. So when we do this up here, it'll be the volume is equal to 1/3 pi, and instead of r squared, I'm going to put an h in for r, so h squared times h is h to the third. And that is my equation. So now we're going to find the derivative. dV dt is 3 times a third is 1 pi h squared dH dt. Right? We remember from implicit differentiation that we are taking the derivative of all of these variables in terms of time. So dt. So we're having to write dV dt, dH dt, dr dt. If we had r, we would do that as well. Okay. So now we substitute what we have, the volume, right? The volume is changing at 100 cubic centimeters per minute, pi h squared, so this will be 10 squared, and then dH dt is what we're solving for. So we're going to end up with 100 over 100 pi dH dt, so that's just 1 over pi, and this will be the height is a two-dimensional object, so this is going to be centimeters per minute. And that is the rate of change for the height of that pile, given those conditions. All right, this is the fourth situation and the final one in this video. We'll get it started and then I'll let you finish it. The diameter of a jawbreaker is decreasing at the rate of 0.1 centimeters per minute. How fast is the surface area decreasing when the diameter is 1.5 centimeters? All right, so we're thinking about a sphere. That's not a very good sphere, but you can deal with it. The diameter, right, goes straight across. That's the diameter. So we're looking at the diameter is decreasing, negative 0.1, and a diameter is two-dimensional, so centimeters per minute, right? We are wanting to find the surface area. How fast is the surface area decreasing? So I'm going to call that ds dt for surface area, and you might just make a note that that's surface area. Okay, when the diameter is what? 1.5 centimeters. Okay, so I need the surface area. The surface area of a sphere is 4 pi r squared. Okay, Now, that's interesting because they're talking about diameter, and yet the formula for surface area has radius in it. So we need to think, well, diameter is how many radii? Diameter is 2 radii. So a radius then is going to be the diameter divided by 2. So now we have a substitution that we can put in here, and we need d rather than r. So s is going to equal 4 pi, and instead of r, we're going to have d over 2. Okay, so I'm going to start up here at the top. S equals, I'm just kind of making this nice, this is 4 pi over 4 times d, right? It's 2 squared, right? This is 2 squared and then d squared. Oops, I forgot the d squared. That was good that I looked back at that. So this should be d squared, right? So this will be s equals pi d squared. Now take the derivative. All right? So I'm going to let you finish this problem, see if you can do it, and get an answer. Don't forget to put the correct units on it, and I will see you in class.